think everybody's on now. So welcome to our presentation, the new approach for brace frame in tilt-up construction. So for those of you who don't know me, my name is Tom Liu from Orange County office here. And today we are fortunate enough to have Brian Cunningham from CORROSION to join our presentation today. We will start off to let Brian to introduce himself, and he will start the first part of the presentation, talks about how the basics of the BRBF and then the advantage of using the BRBF design. And I will take it over and talk about the economics of the BRBF system and how the BRBF can improve the warehouse functionalities. All right, so I will turn the presentation to Brian. Go ahead.
So as Tom mentioned, my name is Brian Cunningham, and I'm a project engineer at CORROSION. And we are based out of the Salt Lake City area in Utah. And as Tom mentioned, we did a presentation at the Tilt-Up convention in Atlanta about these braced frames and some of the economics and performance advantages of using BRBs over other braced frame systems. So that's what we're going to show you guys today. And then Tom mentioned, if you do have questions, typically those are asked towards the end of the presentation, but you're welcome to jump in and ask any during the presentation if you'd like. So we'll go ahead and get started. You should see the presentation full screen now, correct?
Yeah.
Okay. All right. So this is kind of what we'll talk about. We'll talk about the basics of the BRBs and how they work, the structural design advantages of a BRB and the economics of those systems, and then how they can improve warehouse functionality. So in typical building design, you have a gravity system, but then you also have to design for a lateral system, which would be wind or earthquake. And so some frame designs that you can do are an ordinary concentrically braced frame, special concentrically braced frames, buckling restrained brace frames, and moment frames. Here's an example of a braced frame test that shows just a hollow steel section in HSS and the lateral movement. If you look over kind of on this left side, when the brace frame starts moving, it buckles right there and causes a really weak point in these bracing members, which causes it to fracture. This side is still stretching and compressing a little bit, but ultimately the brace buckled in the compression. And for a lot of these members or these brace frame types, compression is the governing factor because steel tends to buckle in compression, but it's a lot stronger in tension. So here we see that we have some length with a load getting pushed on the member, and we have a critical buckling load, which is calculated as pi squared times the modulus times the moment of inertia over the length squared. But what happens when we reduce that length in half is it actually turns out that length is on the denominator. So we now can get a 4 times capacity increase before buckling occurs in this member. So that's a pretty big increase just by bracing it, one spot in the middle. So if we take that a step further, or a few steps further, and brace it, every few inches or every few feet, we then can create a buckling load or a buckling capacity that exceeds these loads being applied to that member. And so we can essentially eliminate buckling in these members. And then all we're left with is the yielding portion, the stretching and compressing of that steel member, which is just calculated as the area of the steel times its strength, the Fy. So here's kind of what the insides of a BRB looks like. You got the casing on the outer end, a concrete grout fill, proprietary interface material between the core and the concrete, small air gap, and then obviously the core that goes down the middle. There's kind of a side view, top view, that core just runs right in the middle with grout surrounding it. and the interface material to prevent bonding of the concrete to that core. So again, the core that we talked about, it resists all these axial loads. And then the casing that's on the outside, it now resists all the buckling or bending that this load introduces into the members. And here's an isometric view of what the brace is. So the core is this red piece. It pretty much goes from end to end, and that's the piece that gets stretched and compressed. All other pieces remain in an elastic state, meaning they don't deform. And so only that core is what goes into deformation. So all of this has been put into the seismic code and steel construction manuals and building design manuals. There's information for BRBs in each of these manuals. One of the big requirements is that these braces get tested. I know there's test reports to support the design of the BRB that the BRB manufacturer has come up with. So here's we'll show you a pretty interesting video here. This video mimics a live earthquake. Kind of have some rocking motion in the building there. That was the first test. Then we go through a second one. So if you remember, that steel core that's down in here runs through the whole length. So you can imagine that steel is stretching and compressing. You can't really tell, but the other end is stationary just like this on the BRB. Both ends are stationary. So that steel is stretching and compressing. Another test that gets done, that first test was just an axial test. This one you can see it's actually pushing the brace off to the side while it stretches and compresses. And this is called a sub-assemblage test. And this actually helps mimic the frame action, the drift of the braced frame. Because obviously the BRB isn't going to be pulled in straight axial tension or compression. There is going to be some out of plane movement. And so the code requires testing like this too, to test mostly this connection area, the stability of this region when the frame deforms and rocks like that. So again, some similar requirements that engineers like to look for on their drawings, and most of this is required for the code. Again, they want to see the testing, at least two tests, one like the axial that we showed and one like the sub-assemblage to mimic frame action. There's some compression and overstrength values that we'll talk about in just a second that they want to see. We'll show full calculation packages to support this testing, support the design of the brace, a quality assurance manual that we're going to build it the exact same way that we built the tested brace. And then the construction documents from the EOR, they'll kind of list these requirements from AISC 341 on the project drawings to make sure that they get accomplished. So again, jumping back to our yielding example, after we get rid of the buckling, we're left just with the yielding. So let's say we have a core plate that gets tested and it has a strength of 42 kips per square inch, and the area is 5 square inches. Well, that would produce 210 kips worth of force. But what happens inside of this brace is when we go into compression, these side pieces of the steel core actually create some friction inside the brace. And so what we call that during compression is a compression factor of beta. And that gets applied to this 210 kips. And also when steel stretches or compresses, when it strains, it actually gets harder and steel gets stronger as it stretches and compresses. So there's an omega factor for the strain hardening. And so both of these factors get applied to this 210 kips to calculate an ultimate force that the brace is going to exert on the brace frame members. So it's called an adjusted brace strength is what occurs there. So for various strain levels, as the brace stretches, we've tested many braces that actually show what this beta factor does as the brace stretches longer. So we can accurately predict the beta and omega factors for new projects based on our previously tested braces. And so that's what these curves do, is tell us, okay, if we're going to strain 2% on this project, we would have an overstrength factor of omega of 1.5 about. So we use that to help the engineers on the projects understand how the BRBs are going to perform in their frames. So it's kind of the technical overview of how braces work. We definitely have some more info on that if anybody is interested, along with calculating the stiffness factors of braces and resiliency of BRBs and things like that. Just some quick kind of connection options that you can do with braces. The bolted splice plate was an earlier design. Core brace doesn't really use that anymore. We typically just do a bolted, welded connection or a pinned connection. And the difference between those can vary with the economy of the connection, the appearance, and the performance. So they kind of all work together, and some are more expensive than others, and some perform better than others, etc. As far as the case or the connections look like this for a welded brace, and this is the gusset plate, and then you have a pinned connection here and a bolted connection there. Looking at the welded connection just a little bit closer, the performance is pretty good. The economy is really good on a welded BRB. There is some field welding that occurs along here and around there, but as far as the brace goes, it's a little bit cheaper to produce. It looks a little more simple than some of the other connections. For a bolted connection, the performance is really good because the connection is centered right in the casing. We get a little more of an economical design with the casing. A lot of people like the looks of the bolted brace, so it's probably the most popular brace that we fabricate. Pin braces are used a lot for aesthetics and exposed areas, kind of like this picture shows. They look really good, they perform really well, but their economy is a little bit lower, and that's because the braces require machining. So AISC allows a 1/32 inch tolerance on the difference between the brace hole and the gusset plate hole. So it's very high tolerance. Some of the erection costs can be a little bit more. Because some of these gussets may need to be field welded to actually get these braces installed with how tight the tolerances are. You can see kind of on a gusset plate comparison, the pinned braces usually produce a lot smaller gussets. So sometimes if this was up in like a ceiling, architects might like that because we can hide the connection a little bit more. So sometimes we'll do those, but they do produce a little bit thicker gusset plate, as you can see, because these braces bear on a smaller surface area than each of these bolts do. As far as casings go, we can do square casings, round casings, or even rectangular casings. So sometimes those play into aesthetics or performance of the brace. And we can also obviously paint them, galvanize them, or even build a stainless steel BRB. And we have obviously tested all those different connection types and steel types and finish types, and they all perform really well. There's no issues with the different galvanizing or stainless steel. For engineers, a lot of these BRBs are actually built into different modeling software. So RAM has BRBs built into it, and engineers can model the braces, right off the bat and get a pretty accurate representation of how the BRBs will help the building performance. ETABS can do the nonlinear models and the linear models, and BRBs are built into that software as well. And it can provide all sorts of information for the engineer to kind of finalize the design. A lot of architects also like using REVIT families to be able to visualize what these braces are going to look like. And here's showing, this was showing a bolted brace, here's showing a welded brace. Even the pinned braces can be modeled. One thing that's really nice is that you kind of see this gusset and how the architect really wanted these tapered gussets in a certain shape. So that can all be modeled within REVIT and other modeling software. And then out in the field, you come up with exactly what was modeled. And so a lot of architects and engineers really like to be able to visualize those things before they hit the field, obviously. Some of the structural design advantages for the frames, you can see here is an example of an HSS section of 16 by 16, where these were designed for the compression member, because again, steel is weaker in compression than it is in tension. So you usually size your member for that compression. When a force is applied across the frame, you get the frame drifts. This member's in tension, this one's in compression. If it exceeds the critical buckling that we talked about, you'll start to see buckling in the casing. And also, because this one's in tension and it's built, kind of overbuilt on size, it ends up pulling down on this beam. And so you get a really negative downward force on the center of your beam. And when this buckles and things like that, produces an unbalanced hysteretic behavior. And like we said, you have unbalanced tension and compression. So at the BRB, you actually have the opposite. So when that force is applied, these braces have nearly similar strength in tension and compression because the steel isn't buckling in the compression member and it's only yielding in the tension member. So we only have yielding left over with both of these. So your frame stays, there's no buckling in your members, and there's actually a small upward force which counteracts the gravity loads that you have on that beam. So you have balanced hysteretic behavior and balanced tension and compression. When those are graphed in tension and compression, you get this with the HSS for when it buckles and gives way, but the BRB is a smooth transition during that yielding between tension and compression. So it's very predictable compared to a traditional brace. And you can measure the ductility of the brace, which is basically how much it can yield and absorb energy. And the BRBs can absorb a lot more energy than a traditional brace. And one way that the code recognizes that is through this R factor. So a BRB system gets an R of 8, which is the highest R factor that can be applied. SCBFs are 6. I think OCBFs are 3.25. So they get pretty low. So with building height, you can get a lot more lateral system performance out of the BRB at higher building heights. And this can translate all the way down from, or all the way from like your roof heights down to your floors, and even into your floors with the footing designs. So quite a bit less load that gets introduced to the buildings because these BRBs are ductile, they give way, they absorb energy, and so engineers are allowed to design buildings for smaller loads because the BRBs help absorb those loads a lot better. Tom, this is you, right?
Yep. Can you?
Yeah, let me switch the screen over for you. And then Tom will take it from here. Oh, there's a long list. Tom, are you still the communications one?
Yes.
Okay.
All right, let's talk about how BRBF can save money in your buildings and constructions. So here we're looking at the multi-story X configuration brace frame, and on the left side we have the BRBF, and on the right we have the ordinary concentric brace frame. Due to the R factor difference, like Brian mentioned earlier, you will have less seismic load coming into the BRBF system compared to the OCBF system. So you can see here, I have much smaller beam size and column size compared to the OCBF system. And also because the compressive capacity and then the tension capacity is same for my BRBF system, so I would end up with much smaller size of the diagonal compared to the OCBF. So for the chevron configuration here, you can see the difference is even bigger. This is due to the unbalanced load. You have to design it for the brace frame, for the ordinary concentric brace frame. So for the BRBF system, since the tension capacity is almost same as the compression capacity, so my unbalanced load is relatively smaller compared to the OCBF, and it's much easier to design my beam to support the unbalanced load compared to the OCBF. Sometimes when you design the OCBF beam for the unbalanced load, you might end up adding like a zipper column in the middle of your bay to take the unbalanced load. And here we have the gusset plate for the ordinary brace frame. Usually ordinary brace frame will have a big, ugly gusset plate at each end. You have to develop a bend line, for your gusset plate for the outer plane buckling effect. And usually you have to offset your window and walls to give the clearance for the gusset plate to bend outer plane wise. And usually the weld length is much longer for the BRBF. No, OCBFs at the gusset plate. Compared to OCBF, with the BRBF system, you have much smaller gusset plate, and usually you don't need a gusset stiffener, except for the chevron and V configuration. And usually the weld length it's much smaller for the gusset to beam and gusset to column. And also since the outer plane effect, it's really small for the BRBFs. So usually you can place the brace frame right against your windows or your walls. So for the footing design, due to the R difference, you have much smaller load coming to your BRBFs compared to your other brace frames. So with a smaller seismic load, you will end up with a smaller pad footing to resist the uplift load. And with a smaller pad footing, you will have you have less rebar to lay out in the field that will cut down your time, your labor. And also for the typical tilt-up warehouse, we use bolted connection for the BRBF. And usually they just torque the bolt per the AIC spec. So that will cut down your crane time, your labor in the field, which is a lot of savings. So now we talk about some of the projects we have done with the BRBF design. The first one here, it's the 633,000 square foot warehouse building in North Las Vegas area. So in Vegas area, my seismic load, my SDS, it's 0.415, so which is not too high compared to California, but the seismic load slightly governed the design compared to wind. And with this building, I have a core area of 5.5 square inch. So that come out to be need a casing of HSS 12 by 12 by 5/8, and I need to. So with that core area, I have an unbalanced load about 80 kips that's pointing upward. So I have to design my beam to span 60 feet to take that unbalanced load, So I come up with a beam size of W30 by 148, and then for the pad footing, I just need a 14-foot square by 48-inch pad to resist the uplift flow. What if we're doing this with a special concentric brace frame with the same configuration? I need a diagonal brace of HSS 14 by 0.625. And with that diagonal, I have an balanced load of 700 kips that's pointing downward. It's almost impossible to design my beam to span 600 feet to take that unbalanced load, even with a heavy W40s or W44s. So what we usually do is to add a zipper column in the middle of my bay to take that unbalanced load. And my zipper columns also need a like W14 by 176. That's a pretty heavy column to take an unbalanced load. And I also, on top of that, I still need a pad footing under the zipper column to take that load. So I also need a like 12 and a half square by 24-inch pad footing. And on top of that, I still need my pad footing at each end to resist the upward load. And that pad footing will be even bigger because I have more seismic load coming to this system with out of 6. So when we do the cost comparison here, I spend a little more on the steel beams, but then I save a lot of steel on the columns. And so it comes down to be total saving about 4,500 pounds of steel. And then for the pad footing, I'm able to save about 111 cubic yards of concrete. And this cost does not including the saving in the connections, your strut beams, your extra rebars in your footings, and also not including the savings, the fabrications and erections. So what if the project's in the high seismic area like California? So the higher the seismic load, the more saving you get out of it by using the BRBF system, because your seismic demand for your structural frame and connection will be always increased 33% if you use SCBF, just due to the R difference. And also your diagonal capacity for your SCBF usually caps out around 300 kips for the warehouse building due to the length. And sometimes we may require additional base of brace frames to take out the load because, again, my diagonal capacity usually cap out really quick in the high seismic area. So for the low seismic area, when you're using the ordinary concentric brace frame, your brace will end up picking like a heavy diagonal brace, due to the slenderness ratio requirement that you have to meet, for seismic design. So a lot of time, and even you using the ordinary concentric brace frame, you would just end up with a heavy brace, diagonal brace. So the next project we talk about here, it's the project Wuring that's in high seismic area, California. It's a 720,000 square foot warehouse building. For this building, we actually use special steel truss moment frame that's out of 7. And with a special truss moment frame, I need 8 bay of those special truss moment frame. Total, almost full line of the building. My column size is W40 by 362 and W40 by 249. This is because I have higher seismic load, and I have to design my moment frame to accommodate the story drift. So you end up with like a heavy columns, and also need a tie beam, gray beams at each bay of the special truss moment frame. Those grade beam will be 3 foot 6 wide by 4 foot deep with a 6 number 8 bars top and bottom continuously. So that's a lot of rebars when you think about it. And also on top of that, I still need my pad footing under the grade beam to just take out the gravity load. So what if, so this is the column size, actual column in the field. You can almost fit 2 people in there. So what if we're doing this building with, BRBF design? I would just only end up with 4 bays of BRBF, and my core area would be 6-inch square. And with this core area, I only need a beam size of W30 by 178 to take out unbalanced load. And then my column size would be the typical, the brace frame column size W12 by 96, versus W40 by 362 in the special truss moment frame. That's a huge difference. And I just need a typical pad footing at each end of the brace frame to take out my uplift load. So when we do the comparison here, I'm able to save over 100,000 pounds of steel by using a BRBF system. And then I'm able to save 244 cubic yard of concrete by not having those big tie beams at each bay of my special truss moment frame. So just FYI, one lines of those steel truss moment frame cost about $800,000, and 4 bays of my BRBF will cost a little over $200,000. And again, this is not including the saving the connection, your strut beams, and all the rebars that you don't have to put in your tie beam. So I know a lot of you doing projects in the high seismic area, but maybe once in a while you get a project in the low seismic area. And I know sometimes you will be asking to use some moment frame in the warehouse building in the low seismic area. So let's use the same configuration. What if this project was in the low seismic area? Assume your SDS is 0.06. You're in the seismic design category A. Usually that's in the Texas area or Arizona. And with this ordinary truss moment frame with out of 3, I still need a column size of W24 by 207 to accommodate the story drift. With a BRBF system, I only need 2 bays of the BRBF system total, and then my core area is 4-inch square, and typical column size W12 by 96. So even just by looking the savings in the columns, I'm still able to save over 50,000 pounds of steel. Again, this does not including the savings in the erections, your rebars, connections. So what's the bigger picture here? So it's pretty expensive by using your special truss moment frame or steel concentric brace frame with a zipper column. So if the building owner or the architect doesn't need to have a fully open bay, it's better to use the brace frame, the BRBF system. So after we talk about the cost saving in the BRBF system, now we start talking about how BRBF can improve the warehouse functionality. So first, it's so obvious that no zipper column required for my BRBF system. So you save extra column there. And without the zipper column, and then now it'll allow me to put, have the flexibility, put like a double door, drive-through door openings at a brace frame bay if you have full height partition in the middle of your building. Or sometimes if your building is tall enough, it's even possible to have like a speed bay occurs at the brace frame bay. So basically the speed bay means in the warehouse, you can have the forklift drive through the brace frame bay. without any issues. And also for BRBF system, it's better option for longer brace. So nowadays, your warehouse building, the clear height's getting taller and taller. So unlike the OCBF system or the SCBF system, with the BRBF, you don't have the slenderness ratio requirement. It's almost, you can have any length of the diagonal you want, and they can, as long as they can manufacture it. And in this building, you can see how long those diagonals are, and then here's the average size construction people. And also with a BRBF system, you end up with a smaller column size and smaller casing size, which means that it's easier and more flexible for your racking guy to lay out the rackings. And if your architect end up putting a demising wall, full height demising wall in the middle of your at your brace frame line, you will end up with a much smaller wall footprint because your diagonals doesn't interwrap with your warehouse spacing. Look, here's the typical BRBF column versus your steel truss moment frame column. That's a huge difference right there. So also I know that Corbrace has come up with some smart device that you can install in your BRBF diagonals, and I'm gonna pass on to Brian to introduce this a little more, and he will finish up the rest of the presentation.
All right, thanks, Tom. Yeah, so as Tom mentioned, we can basically build any length brace needed for a project. A lot of times we're limited to the length of the plate that the steel will roll, or the steel mill will roll. And so a lot of times that's 600 inches or 50 feet, but we actually have braces as well that can be spliced in the middle of the brace and either assemble the two pieces in our shop or assemble the two pieces at the job site. And so, yeah, we have some braces out there that are over 70 feet long and of pretty high capacity. So with BRBs, you can do quite a bit more for really long BRBs, like Tom mentioned. And also, BRBs are starting to become, well, as they say, smart BRBs. You can actually install an actuator similar to how the BRBs are tested in the labs. You can actually have these installed either on the exterior of the casing or the interior of the casing inside the concrete grout. And so what that allows you to do is it allows it to track the yielding or the frame action during an earthquake. And that data can be downloaded and analyzed immediately after an earthquake. And we've done quite a bit of what we call resiliency testing. So testing basically the life of the BRB and how much life is in one. And that data from these recorder devices, is what we call them, can be analyzed in helping determine the useful life of the BRB and what's left in it. So it's pretty cool that we can combine the technology that's used in testing to an actual project and out in the field. So just a couple other things. As far as what kind of structures BRBs can be used in, obviously they're used a lot in tilt-up construction because of the length of the braces and the slenderness ratio that Tom mentioned. They're also used in a lot of prefabricated metal buildings. So they can go kind of along the exterior to help provide that strength. Stadiums use them a lot higher capacity braces for all the directions. Other stadiums up in Canada, obviously office warehouses and mixed use buildings. There's some really nice pin braces that were probably exposed in this project. And also parking garages. it can help stabilize all those. So that is kind of the presentation that me and Tom have. Did anybody have any questions for us at this time? Is there anything else you'd like to add, Tom, to that?
No, I don't have anything to add to anybody. Nobody has any question. Well, I guess if anybody has any question, you guys can always feel free to contact corporate directly, or
you can also contact Tom, obviously.
I would just end up contacting you anyway.
Yeah, but yeah, either way, you can contact Tom or me if you have questions on BRBs. Like I mentioned earlier, we do have more technical presentations and design guides and kind of tables for initial designs of buildings. But Tom knows most of that too, because he's worked a lot. Yeah, go ahead.
This is Lisa in San Diego. I guess one question was like, what's the highest capacity brace you've ever installed?
So I believe the largest core area we've done is 46 square inches. I don't know the total capacity, but if we did the 46 times 38.
That's about 1,500.
Yeah, about 1,500 kips, 1,500 kip brace. So a lot of these tilt-up warehouses that we've kind of shown you in this presentation, they're somewhere in the 6 to 8 square inch range. So comparatively, a 46 square inch is pretty big.
Yeah, that is big.
Yeah.
Okay, and then my question is if there's anything up and coming for the next code cycle that we should know about.
That is a great question. There are only a couple of things, and most of them don't really affect how we design or how you would design using BRBs. I know we have a little Word document type up of every little thing and where you would find it, but a couple things I can remember off the top of my head are the beta factor is now allowed to go up to 1.5. It was previously 1.3 was the maximum. I think the connection factor is reducing. There used to be a 1.1 connection factor. They're eliminating that from the 16 code. Core Brace has, for the meantime, we've arbitrarily opted to keep that connection factor for right now. It's not a big factor anyway, but we're just keeping it for gusset design and the weld design of the gussets. But yeah, I could send over that list to Tom, and then you could take a peek at everything that's changing as far as BRBs go. That's a good question, though.
Sure, great, thanks.
I have a question. Can I go ahead?
Yes.
Yeah, go for it.
Question comes from Istanbul. This is Yusuf speaking. I'm surprised hearing that the cross-section of the BRBs could be either round or rectangular or square. For rectangular cross-section sounds strange to me in terms of buckling risk under compression forces.
Correct.
What is the main reason for selecting the rectangular? Because considering the out-of-plane buckling, it doesn't make sense to decide the rectangular section. What do you think?
Yeah, you're exactly right, actually. The main reason why a rectangular casing could be used is a lot of times either the architect or engineer has designed the BRB to fit inside of a certain wall cavity size. And so a lot of times we're limited on a horizontal dimension of, let's say, 10 inches. But vertically, we can basically do any size brace. And so doing a rectangular casing is very inefficient economically, because you're exactly right. You don't get a lot of out-of-plane horizontal resistance going more vertical, but you do get some. And so I have a project right now actually that we're doing 10-inch wide by 14-inch tall casings in order to fit inside of a wall cavity. Whereas if we could have done a square, a 12 by 12 square would have worked and been a lot cheaper. But because we were only had 10 inches available, we had to opt to go vertical to try to get that little bit more capacity for the bending on the casing. One other quick thing about that is sometimes if a really large core area, say like a 20 square inch core area, needs to fit inside of a wall, like between an elevator shaft and a stairwell, we've actually taken the 20 square inch, cut it in half to 10 square inch, and built 2 BRBs to fit in between that cavity, and then they share gusset plates. So that's another option instead of doing the rectangular casings, is if you get too big, you could split the BRBs and use them in that wall cavity. Does that answer your question a little bit?
Yeah, I think it makes sense. I understand. By the way, it was a very nice presentation. I'm impressed to see, especially those applications for the tilt-up structures. I have another question. Can I go ahead? Can I continue? Okay. My second question is related to the post-earthquake damage assessment. If we are dealing with friction dampers, we don't have to worry about that because of the long distance capacity of the friction surface. But considering the BRBs, it is critically important to measure what the elongation is inside the system, especially after the MCE event. So we need to make sure that the capacity is still reserved for that. So monitoring the post-earthquake damage sounds like an important matter. What do you think about that?
Yeah, no, it definitely is, and that's one question that a lot of building owners will have after an earthquake is, well, what's the what's the lifespan of my building now that it's gone through an earthquake? And if the BRBs did have that recorder device installed, we would know exactly what happened in those braces and along that line of resistance. If they don't, it could still be approximated probably somehow through marks on the braces or marks on the building and trying to determine how much the building actually drifted and things like that. But yeah, definitely with those recording devices, we can get a very accurate picture of what actually happened in that building and how much more life those BRBs have. One kind of side topic on that is through some of the testing we did on the resiliency of BRBs is, we've found that they are very resilient, meaning they can, outlast the AISC protocols and many of the earthquakes that have already hit California in recent years. We've sent them through those same protocols, and they've lasted quite a while. So it's good to see that the BRBs perform well and can perform multiple times through many earthquakes. So
yeah. Once I asked this question to the inventor of the BRB, the Japanese professor, Mr. Wada, and he told me that per the preference of the designer, the BRB could resist until several MCE events. So I understand as long as the capacity is sufficient enough for, let's say, 2 MCE events, maybe we don't have to measure the post-earthquake damage. Don't you think so?
Yeah, I would agree that the BRBs, they're definitely designed to not only, be a life-saving measure for the building, but they're designed to last forever. And well, not forever, but they're designed to last for multiple earthquakes. The resiliency testing we did put it through the Northridge earthquake, and it lasted like 20 earthquakes before it fractured. So yeah, these BRBs perform very well, and it can perform through multiple earthquakes. Just depends on the earthquake and the location and how it hits the building and things like that that aren't fully known after the earthquake. But some evaluation can help figure that out.
Yeah, thank you very much. My last question, I don't want to take your too much time. My last question is regarding 181 Fremont Tower. As far as I know, it was used a hybrid type BRB together with viscose dampers. Is that a core brace application or another brand name?
Yeah, so I think what those are kind of called is like an outrigger brace.
Yes.
And I believe I didn't work on that project, but I believe it had basically a 4-pack of BRBs together. So we built 4 regular braces, packed them together in a gang, and then it was assembled as part of that system. So yeah, it was regular BRBs that were built to resist those lateral loads.
So they were core brace applications, right?
Yeah, I believe so. I know the building. I just don't. Do you know when that project went up? Do you remember what year that went up?
Yeah, it was completed last year, and it won a great prize this year from CTBUH.
Okay. Yeah, so Core Brace probably did it. I know Star Seismic did a few outrigger braces like that as well, but yeah, I believe they were Core Brace BRBs on that project.
I see. Thank you very much, guys. It was a very nice presentation.
Yeah, thanks for the questions as well. Does anybody else have any questions for us? Okay.
You're none?
Well, Tom, is that?
Thanks, everyone. Thank you, Bri, for joining us.
Yeah, it was good. Let us know if you have any other questions. You can send us emails or whatever you guys need.
That's always helpful.
All right, well, that's it. Then we'll sign off. You guys have a good day.